do something. So we'll share the last session. So the last but not least, for sure. And so it's a pleasure to listen to you, Chris, from, say, almost a neighbor from Saclay. So the floor is yours.
Thank you. Thank you for the invitation, and thank you all for staying to the bitter end, or almost. Right, so I'm going to talk mostly about phonons, and maybe I forgot a word here. I should have said simulating other quantum fields in the lab. And maybe that's a little bit of a misnomer, because the only other field I'm really thinking about is the electromagnetic field. And the point of departure is going to be nonlinear quantum electrodynamics. That is to say, nonlinear effects, such as some that I've listed here. There are experiments going on right now on things like light-by-light scattering and the birefringence of the vacuum. Those are terribly interesting experiments, but I don't know much about them. This is what I want to talk about. I'm going to talk. We've already heard a lot about black holes and Hawking radiation, so I'm going to say a little bit about that. I don't have much to say about real Hawking radiation, but I'm going to talk a little bit about acoustic analogs. That is to say, how to use phonons to imitate at least some aspects of what goes on in Hawking radiation. And then I will move to another nonlinear effect called the dynamical Casimir effect. I'll describe what I mean by that, and its acoustic analogs. This is actually something that my group has worked on quite a bit. The Hawking radiation stuff is actually mostly not mine, but I think it's interesting it sort of motivates a lot of how we got started with this. And an important thing that we've already heard about is the information paradox and the black hole information paradox and things like that, and the fact that you make pairs of particles and they might be entangled, and so what I want to talk about at the end is fairly recent results that we've had on entangling particles, but it's not going to be about photons. It's not going to be about phonons either. Although in the phonon, we hope that what we're developing here with looking at entangled atoms might be applicable to entangled phonons in the future. Okay, so black holes. There's a picture you can load off the web, which is just evocative, doesn't probably contain any important information. And so there's this famous paper written by Hawking in 1974 entitled Black Hole Explosions, in which he discussed the fact that, at a black hole, if you try to think about quantum mechanics, it can emit particles, and it will do it in pairs. One particle will escape and one will disappear into this black hole. And he didn't actually write it that way, but as a quantum optics guy, it really sounds like it's a parametric oscillator. It's a thing, or a parametric amplifier. It's a thing that produces, that is somehow activated at one frequency and produces excitations at other frequencies. And the first equation that's in this paper that I just copied right in here is this relationship between outgoing quantum fields and ingoing ones. These are operators. And that's just the Bogoliubov transformation, which comes up over and over again when analyzing parametric oscillators, as well as many other interesting nonlinear aspects in physics, such as what happens in interacting Bose-Einstein condensates. Okay, so I don't know much about general relativity, and I don't know much about black holes, but I think I know a little bit about parametric oscillators, and so I want to now run with this, and many other people in this field have tried to run with this, to see how we can push this analogy using the tools of quantum optics. And in particular, we're very interested in this entanglement question. one way of putting the black hole information paradox, I think, somebody will correct me if I'm wrong, if you have these particles that are being created in pairs, they're being created like a parabolic oscillator, that is to say in entangled pairs, one gets out, one disappears. However, if you really believe in quantum mechanics and entanglement, there's information, there are correlations between the two particles which you can experimentally learn about. So does this happen in a black hole, or does the information that went in there really disappear? So I don't know, but what we can think about is an analog, an acoustic analog, where instead of creating phonons, we create instead of creating photons, we can create phonons. And in the case of phonons, we can actually create horizons that we can go out to either side of, all right? And then we could, in principle, have a look at whether these things are really entangled and play quantum optics games with it. And I'm almost sure that we will find that they are correlated. And this was inspired, this began with the paper that I've shown up here. Bill Unruh wrote this paper called Experimental Black Hole Evaporation. He toned it down from explosion to evaporation, which was probably wise. And the idea was that that Hawking radiation has sort of a classical, it's in a way a classical effect, or has a classical analog, which occurs when there is a transition between a subsonic and supersonic flow in any fluid. This transition point looks like horizon in the sense that any sound or any wave that is emitted here, any wave that is emitted here in this direction has no way of ever getting back. So that looks a little bit like a black hole. And so you could actually realize such a thing in the lab with just a tank of water. If you have water flowing through a thing that looks like this, where the depth of the water changes, what happens is the flow speed will increase, whereas the speed of these waves will decrease, and you can actually engineer without too much difficulty such a transition. And so now you've got a black hole, or a dumb hole, if you think acoustically, and you can study how this all works in a completely classical context. And this has been done by several people. It's not so easy to interpret all the results, but there was a group connected with Unruh himself in Vancouver that published an interesting phys rev letter. And there's a group in Poitiers that has been working on a similar thing, and they think they can do even better than this experiment. And there's a lot of work going on about that. But I'm not going to talk too much about that. I'm going to now go to what I know more about, that is to say, Bose-Einstein condensates. You can imagine that you can create a similar situation in a flowing superfluid. And that's an attractive thing to do because the superfluid, in a Bose-Einstein condensate, you can get the temperature really, really low. And instead of being in a classical regime where this Hawking process is stimulated in fact, these experiments I referred to earlier, one actually sends in waves and looks for stimulated effects. You could hope that you could actually watch spontaneous Hawking radiation, that is to say, the spontaneous production of excitations of phonons in such a system. And the back of the envelope calculation that says that might be possible is that, well, you can calculate a Hawking temperature in a typical situation, and it's in the neighborhood of 1 to 10 nanokelvin if you fiddle the numbers in the correct way. And those are temperatures, at least the 10 nanokelvin, are temperatures that you might hope to reach in an experiment. And so now you have a system where maybe the temperature of the the fluid is actually comparable to the talking temperature, and you might be able to actually see this radiation. And even if you can't really see it, in the sense of observing a thermally distributed bunch of phonons at this temperature, because maybe you can't, maybe the talking temperature will be 1 nanokelvin, and you will, and your BEC is at 10 nanokelvin. It'll be very hard to actually isolate a thermal distribution. However, since you have access to both sides of the horizon, the obvious thing to think about is can't we do correlation measurements to observe the pairs themselves and observe how they behave, how correlated are they? Do they exhibit quantum correlations? Do they exhibit entanglement? And if you can do all that, well, then you're pretty confident that you've actually imitated, at least in some limited way, what happens in a black hole. So here's the, so this is being done. A thing you need to know is that the speed of sound in a Bose-Einstein condensate is given by a formula like this, where A is a scattering length, rho is a density, and m is the mass of the atoms making up the condensate. And actually, all three of these quantities can, in principle, be modulated. You can change the scattering length with Feshbach resonances. You can change the density using by changing the density. It's a compressible fluid. And you can even change the mass of the particles, because you can put them in lattices, and the mass that matters here is the effect. It can be modified because there will be an effective mass of these particles, which you can modify as well. So you have a lot of parameters that you can try to mess with in order to imitate imitate a black hole. And this was the first attempt that I know of that did this was published here. And roughly the experiment looks like this. There was a Bose-Einstein condensate in a harmonic trap. This is a roughly parabolic shape. And on this harmonic trap, they superimposed a laser with a blue detuning, which raised the potential of the atoms. The Bose-Einstein condensate was put in a place like we're noted here with A, I think. There was a fairly sharp step in this potential because the laser was focused, the optics were as large aperture as they could get. And then they moved this trap relative to the laser. I think in the first version this was a magnetic trap. And they could move them relative to each other. That's what this arrow represents. And that meant that this step went past the condensate, or if you like, the condensate went past the step. And that sort of imitates the situation that was imagined here, okay, where there's a change in the flow velocity. There's actually also a change in the density, unlike water. And so you can make a situation where you might hope to, at least on paper, you can produce what do I want to say, which subsonic to supersonic flow situation. I forget which. I'll get it messed up if I try to tell you which side is which. But I will show you actual data. So here's typical data that was taken. Here's the step. I think it's reversed. So the laser is here. This laser step is being scanned in this direction. This is position, and this is now a photo of the atoms in this and more or less in situ picture of the atoms in this situation, in this potential. A snapshot at a given time, and this is simply a cut through the photo. And so this is now the density of the gas as a function of position. And because of this step, the density goes way down when the step goes by. Okay? And so the flow is much higher here, and the speed of light is lower. The speed of sound is smaller. So this is a supersonic region, and this is a subsonic region. And this step happens over, you can see, over a distance of some few microns. Okay, so that's what they did. And now you, in principle, you have access to both sides of this black hole, this dumb hole, and you can actually now look at, a key thing to look at are these correlations. So this is a group in the Technion in Israel, and they worked on, did an awful lot of things, and published in the last couple of years a couple of very interesting papers, one in which they claim to have observed self-amplifying Hawking radiation in what is called a black hole laser. The reason, well, we don't go into too much detail about why that is, but when you, in this situation, when you make a step, there's usually a step in the other direction as well. You make a black hole and a thing called a white hole, and actually the radiation that is, this Hawking radiation that's in there will actually bounce back and forth and act and can be amplified. They observed or claimed to observe that phenomenon. And then in just about 6 months ago, they published another paper where they actually claimed that they had observed Hawking radiation and its entanglement. So and that was done by looking at correlations on either side of this event of this horizon. But the story is not finished, because in this Hawking business, there are an awful lot of people paying close attention and making a lot of ils font du pinaillage. And so the publication of this observation actually stimulated several theoretical works that contested the interpretation of the of Jeff Steinhauer, who was the person who did this experiment, about whether there was really an entanglement being observed. And there are also some papers being published about how, well, this isn't really a quantum effect. Maybe you can simulate the exact same observations with essentially classical effects. And so this is the state of the field at the moment. And I would say that there is some controversy about whether this analog Hawking radiation has actually been observed. We can then ask even further, especially in light of the rest of the talks, some of the other talks we've heard at this conference. Well, even if it's true, or we learn how to do this better. And by the way, I think in our lab we do have a way to do it better. It's just a little hard, and I'm a little reluctant to step into this controversy without being very sure of myself. An interesting question to ask, which I don't. Well, an interesting question is. So what if we see entangled phonons in a Bose-Einstein condensate due to something that is close enough to the Hawking mechanism? Is that going to help anything for quantum gravity? I kind of doubt it, although I'd be happy to be contradicted. There are several reasons. It's because this is, these analogs are approximations to what happens in a real black hole. For one thing, the dispersion relation of the phonons in a BEC is not linear as it is in electrodynamics. It goes quadratic. It's the Bogoliubov dispersion relation, which is linear at low k vectors, but at high vectors it becomes particle-like. It's just a quadratic. And that messes up, that means sort of trans-Planckian physics that might be present in a black hole are certainly not going to be present here, right? That's going to get cut off by the dispersion relation, and it's just going to become kind of boring particles bumping into each other. Well, I don't think that's boring, but string theorists probably think that's boring. And then there's the question as well, there may be other questions. If you really believe, we think we understand how to describe Bose-Einstein, weakly interacting Bose-Einstein condensates like these very well. Pretty much using the Bogoliubov approximation, we can explain practically everything. And that predicts that there will be entanglement between phonon modes, and maybe that's not a really big deal, all right? And it won't help anybody solve the black hole information paradox. But it's still interesting, and people are having a lot of fun doing this. And the rest of you are having a lot of fun doing what you're doing as well. So, all right. So, like I said, I'm a little reluctant to actually get into this myself with my group because, yeah, there's a lot of controversy, and it seems to be a very emotional subject, and I don't want to get anybody upset unnecessarily. And we've been able to, with help of suggestions, notably a guy named Jacopo Carusotto, to look at other situations that are a little cleaner, a little easier to deal with, and a little easier to interpret. And that is what is known as the dynamical Casimir effect. The dynamical Casimir effect is what? It is a remarkable effect. It is sort of parametric down conversion in the vacuum. You can take a mirror. If you take a mirror and subject it to a non-uniform acceleration, and a simple example is sinusoidal motion, if you make it move fast enough, you can actually generate pairs of photons out of nothing, which is amazing. It's a nonlinear quantum electrodynamic effect. It was actually first discussed in this paper a long time ago. It's stimulated a whole lot of papers, theoretical papers. I recommend a review article that is written by these people, whose experiment I will discuss in a moment, who actually discuss the dynamical Casimir effect and also its relation to Hawking radiation and other similar types of effect, the Unruh radiation effect, among others. So that's a quick introduction. I will just give you a few quick ideas about how to understand this. The first time I heard about it, it seemed just as amazing and counterintuitive as Hawking radiation. One way to think of it is discussed here, that what happens is when you accelerate a reflecting object in vacuum, it sort of bounces off the vacuum fluctuations that are there, and there will be a damping force. And this damping force means that energy will be taken away from this mirror, and it goes somewhere. Where does it go? It goes into these pairs of photons that I just talked about. There's another very well-written, typically clear paper by Astrid Lambrecht and her collaborators in which they discussed a concrete situation in which you make a mirror oscillate, and it's fairly easy to read. And they put it in a cavity, and they actually tried to estimate, well, how many photons can you actually make? And here is without the prefactors, an estimate of the number of photons that this activity can make. And you can see it's very depressing, because there's this V over C in here. So if you actually move V over C squared in here, F is the finesse of the cavity, tau is the duration of the observation. And you see that moving a physical object at anything approaching the speed of light so that this becomes not really hopelessly small is really hard. And so it's really hard to imagine getting any detectable number of photons by doing this, at least in a mechanical way. However, it has been done in an electronic way. There have been actually several different approaches to this, and this is probably the one that is the most has been the most successful, I think. It involves Josephson junctions, which we've also heard a lot about at this conference. What is possible to do is to make as already been said, a squid is a variable inductance. It can be changed by, its inductance can be changed by the flux through a circuit. And if you think of a transmission line, and which is the transmission line? I think it's this, okay? What you can actually do is by changing the inductance, you change the effective node of the node of a wave that is propagating out here. Okay, which means that if you change the inductance, you can actually do the equivalent of moving a mirror. Okay, and since it's now a nano-sized circuit and it's a squid, you can do this at 10 gigahertz, and you can hope to actually get into a situation where you can move an effective boundary for an electromagnetic wave rapidly enough to do something. And then some very fancy detectors, low noise amplifiers and so on, analyzed this and actually claim to have observed the effect, that is to say, the spontaneous generation of two other frequencies whose sum is the frequency of the drive. I don't want to go in that. There are probably people around here who understand this experiment better than I do, but it's a remarkable experiment, and showed that something like this can happen. Then the people in this paper, while they were actually this group of research theorists were actually interested in calculating what would happen if you try to simulate Hawking radiation in a Bose-Einstein condensate. And they noticed that actually, for free, or in part of what in the situation they analyzed, there's actually the dynamical Casimir effect occurs as well. So there's a paper here that they wrote in which they discussed, well, what happens if we don't do this flow business? We don't make a barrier move quickly. We just try to modulate some property that influences the speed of sound. They thought about modulating the scattering length in some sinusoidal way, or not sinusoidal way. And they showed that you get a Hamiltonian that looks like this, that we know and love from Bose-Einstein condensation. These are Bogoliubov coefficients, and you get this thing that looks this term here, and you see the product of two B daggers and the product of two B's, which looks exactly like a quantized parametric oscillator. So that's going to create Bogoliubov phonons at these wave vectors, and that is simply a quantum mechanical formulation of what I just said. A formulation of what I just described for electromagnetism, transposed to the elementary excitations of the Bose-Einstein condensate. And this is what inspired us to get into this game to begin with. So there were these authors proposed that we modulate the scattering length. It turns out you don't have to do that. As I said, I've already given you this formula. There's the speed of sound, which depends on a scattering length, that is to say, an interaction parameter, a density, and a mass. It's actually the atoms that we happen to use. We can't measure. We can't vary the scattering length very easily, but we can measure the density. And so it becomes a very simple thing. What is simply necessary to take a BEC and that trapped in some sort of trap, a laser trap in our case, and modulate its density. And a similar Hamiltonian should obtain, and we can look for these excitations. And so that's what we did. Here are the people who did it. Several bright students who are now have jobs in new places. And I will just briefly walk you through how the experiment works. What happens is we have a Bose-Einstein condensate, quite elongated, in a laser trap. And when we can measure, what we will do is we'll make measurements in momentum space. We will let this thing go. And by the way, do I have another? Yes. Typically what we will do is we will manipulate the atoms and do this oscillation thing, and let them fall onto a detector which is quite far away. And essentially, this detector will allow us to measure both arrival times and positions of the atoms after they've fallen 50 centimeters. And to a very good approximation, that amounts to measuring their momentum distribution. And so what we want to do is there any other important information here? What we want to do is we want to observe whether we can actually produce excitations at plus k and minus k for k vectors, momentum vectors that correspond to the frequency which would correspond to this dynamical Casimir effect. So a few more details. We're using metastable helium atoms which have an internal energy of 20 electron volts, and that's what allows us to do this detection on a microchannel plate. So there are interesting details having to do with the detector, but I don't think I'm going to bore you with too much about the detector. So here are some parameters. The length of this condensate is about 1 millimeter. These are typical parameters, chemical potential and trapping potentials that are used to make the trap. At the end, the condensate or its modification due to the dynamical Casimir effect hits this detector, and here is an artist's rendition of what the detector looks like. The condensate hits this thing, and then we get a bunch of clicks for all these detectors, and I may have an actual example of what that looks like. All these dots are atoms, or represent atoms that hit the detector, and the vertical axis is time, and the horizontal axis is space. So this is some disk corresponding to this condensate, and then what you see above and below are these side bands, which I'm now going to try to convince you are due to the dynamical Casimir effect. Okay, just quick how the experiment proceeds. Well, maybe you don't really need to know all that. We create a BEC by evaporative cooling. We do a lot of atomic physics tricks. And at the end, when we've got our BEC, we simply subject it in, this is the optical trap and its intensity. We simply wiggle it up and down at frequencies of between 500 and 5,000 hertz. Once again, this is the Hamiltonian we're interested in, and we're going to look for different k vectors which land on the detector. Important point is that these detectors, we're going to create excitations with k vectors in the phonon part of this dispersion relation, where it's linear or almost. We don't really detect phonons. What we do is we drop the atoms, we let them hit the detector. As they fall very rapidly, the condensate density goes way down. That means the speed of sound goes way down, and excitations, phonon-like excitations, which have a given k vector, are believed to adiabatically turn into atoms with the same k vector. And we have good evidence that that really works. People refer to this as adiabatic, what is it called? Adiabatic phonon evaporation. A phonon, which actually is a collective excitations of atoms going in different directions, when we slowly ramp down the density, will turn into a single atom moving with a well-defined momentum. And that's the thing we actually detect. So there's a little subtlety in going from the phonons inside a BEC to the objects we actually detect. Okay, so that's what it looks like. That's a single shot. This is the condensate falling down on the detector, and these two side bands correspond to frequencies which are exactly half of the modulation frequency. And we can do quantitative analysis to make sure that that really works. And we're pretty convinced that works. And then we can do a little better. We can not just look at these two side bands, we can actually look at their correlations. So instead of just looking at the density profile, which is this thing in blue, this is the same thing I showed on the previous slide, except it's been averaged many times. So we get nice, good signals to noise. We can measure a correlation function, which is to say we make a histogram of pairs, of all possible pairs in this density distribution, and then average that histogram over many repetitions, hundreds of repetitions, and then normalize it to a histogram of uncorrelated data. And so what you see in red is a normalized correlation function. Right? So we show that these, and this is the same correlation function in a two-dimensional space where I've drawn the two vertical velocities. And so these dots here are the cross correlations between different velocities. So these, in some sense, these particles or these excitations have been created in a correlated way. I don't want to say that they've been created in pairs yet, because there's another step to go to demonstrate that. Okay, so we did all that. So that was all. We were very, very pleased with that. Now there's one more. There are a few more steps to really show that we've seen a quantum mechanical effect having to do with the dynamical Casimir effect. For one thing, you can object that we did not do this in a bath at zero temperature. In fact, the temperature of the Bose condensate that we used had this frequency, had this temperature. That corresponds to a temperature of 4 kilohertz, which is in the neighborhood of the frequencies that we used. Okay, so actually, KT was approximately of order h bar omega. So that means the phonon occupation number was in the neighborhood of 1. So the effect was not necessarily stimulated by vacuum fluctuations. There were a small amount of thermal fluctuations present, and so that's an objection to keep in mind. We tried to look for what you might call a true quantum effect by looking at the number of detected atoms on each side, in each of these side bands, looking at the difference and trying to determine whether this difference was actually sub-Poissonian. If they're actually produced exactly in pairs, that means every time there's a particle here, there will also be a particle there, and this difference will go to 0. This difference will go to 0, as will its variance. Right? It doesn't really go to 0 because there are all sorts of other noise things, one of the most important of which is finite detector efficiency. But if it's really working, we ought to be able to get this normalized variance to go below 1. Okay? Here's our attempt to do it. This is the normalized variance as a function of the position of one of these boxes. So we count the number of atoms in this box and in this box, and then we move this box back and forth, and we plot the result. Okay? And the orange is this difference. And you'll see we were very disappointed to see that this normalized variance does not go below unity, which means that we cannot really exclude the fact that all we've done is produce classical waves that happen to be correlated. It's not surprising that if you shake something like a BEC or a tank of water, for that matter, that waves will go out in opposite directions in a correlated way. Right, so that's an important thing we'd like to improve in a future experiment. Okay, so that's where we are now. And now I want to go into talk about more recent things where and change gears rather drastically. I'm going to stop talking about phonons. There aren't going to be any photons either. I'm just going to talk about atoms. Right? We've been developing ways to measure, to produce and measure an entangled set of atoms. And like I say, you will see that what we've done can probably be transposed to the phonon regime if we ever manage to observe a non-classical phonon excitation. Okay, so there are the people that do this, and you'll notice one of the people is Alain Aspect, who has been very excited whenever we have started talking about entanglement and in particular Bell inequalities. So I'm going to talk to you about how you might measure a Bell inequality, observe a Bell inequality using these kind of techniques. Okay. We have another source of atomic pairs that produces two bands like this. Here I've plotted in velocity space. It doesn't have anything to do with the dynamical Casimir effect. We didn't shake the BEC in the way I did in the previous slides. We do something else, which I'm happy to describe, but I won't go into for the sake of brevity. But we can produce shapes like this, two bumps in a density distribution, in which we have good reason to believe that what is in this bump is correlated with what is in this bump. In particular, each blue trace is correlated with a red trace on the other side. Okay, so we can actually do cross-correlation functions. I won't show them to you, but they're in very much the same spirit as I showed you for the dynamical Casimir effect. And we've convinced ourselves that these two classes, what I call P and minus P, are correlated, as are P prime and minus P prime. And if the whole business is coherent, it should be possible, if you can filter out these different velocities, it should be possible to create the following state. A state which consists of one pair of atoms, which is in a superposition of different momentum states. That is to say, one atom, how am I saying this? One atom is one pair has P and minus P, but it's in the superposition of being that and P prime and minus P prime. So that is a nice entangled state. So we can look at correlations and determine this correlation, and we can now also try to see if this coherence, if this is really a coherent superposition of these two different pair states. Right. And to do that, we can make the following type of interference experiment. In order to see this coherence, we've got to see a phase, so we have to measure some kind of interference. And here it is, and this is actually a variant of a Bell inequality experiment. Okay? There are correlated pairs, P correlated with minus P, and P prime correlated with minus P prime, and one pair is in a superposition of both of these. Okay? And if you do that, you can now use Bragg diffraction, use lasers, to deviate these paths and cause them to mix in such a way that one momentum of one pair and another momentum of the other pair can be mixed on this beam splitter, and therefore their origin be erased. As well as the opposite pair on these two beam splitters. Oh, by the way, I didn't say how do you select the momenta that you want. You select it with the detector. You simply let everything hit the detector, and we will only analyze the data that falls in these velocity bins. Okay, so the detector is actually detecting all the atoms at once, and it is post-selection that allows us, post-analysis that allows us to choose which of these momenta we use. And now, if you do this and everything is uncorrelated, what you expect, well, first of all, what you expect is that the probability to detect a single atom in any one of these ports is independent, is always 1/4. Is always 1/2. There are two particles and there are 4 output ports. And this is independent of any phase that could happen inside these interferometers. On the other hand, and this is essentially the idea of Bell, or maybe I should say of Clauser, Horn, Shimony, and Holt, that there is a correlator between different outputs that is written in this way. The probability of detecting a particle in A plus and B plus A minus and B minus and A minus, et cetera, et cetera. That's a little complicated to get your head around. But this particular correlator will not vanish if the state is indeed this Bell state, this entangled state. And so what we can now do is we can actually try to observe this correlator and see if we can observe and can demonstrate that there's an entanglement. And we can do this it's actually, what you really want to do to observe a Bell's inequality is you need to change the phase, the relative phase of these paths over a certain number of different parameters. Okay? We can't, at the moment, we can't really do that. We don't have complete control over all these phases, but these Bragg diffraction gratings can actually give us a little bit of control. We can vary a little bit the relative phase of these paths of these two interferometers, and we can actually try to see if we can get this correlator to vary a little bit. And so here's the result, the current result, and you should mostly look at the bottom graph. These are the individual probabilities that have been summed and subtracted in the right way to produce this correlator. And you can see that in some cases, we can actually get this correlator to substantially differ from zero, I'm sorry. And so we're actually fairly confident that these are different data sets that were done for different conditions of the diffraction gratings. We are tempted to assign phases to these, but we're not completely sure we can't guarantee that we know all the phases that are involved. So the thing you should really just look at is the biggest deviation, which seems to say that we have some non-trivial deviation from completely uncorrelated data. So we believe we have something, well, it is at least consistent with having produced this entangled state. New data is on the way. We hope to actually be able to observe this as a function, as a deterministic function of the phase difference. That's coming, but it isn't ready yet. This is where we are at the moment. So that's all I wanted to say, and I'll just tell you what's on our list of things to do. Like I said, we want to do this experiment with well-controlled phases and actually observe this correlator vary in a controlled way. That would make us really convinced that we're observing what we say we are. By the way, if this correlator goes above 1 over the square root of 2, above 0.7, then it will be possible to go one step further, combine it in the appropriate way, and actually demonstrate that we can violate a Bell's inequality. But remember that just demonstrating entanglement should be easier than seeing a Bell's inequality. Bell's inequality is violating Bell's inequality is a particularly strong form of entanglement. And there are many other kinds of entanglement that are not quite so strong that would be interesting as well. So the other thing, next thing to do would be, it would be interesting to actually violate Bell's inequality, to improve the experiment enough to do that. That's probably pretty difficult. But that would be interesting to do, to take freely falling massive particles and see if Bell's inequalities still work. Between you and me, I believe they will still work. But it's something to test, and that has never been tested. And then we want to go back to this dynamical Casimir effect and sort of play the same tricks and see if we can actually see a sub-Poissonian effect, which would say we actually have a quantum correlated pair. And once we can do that, we could actually apply the same technique to demonstrating the entanglement of the dynamical Casimir effect. So that's already a couple of PhD theses. And if all that works, someday I would like to go back after this Hawking radiation problem, produce a horizon, see the pairs, and see if we can't do essentially a Bell's inequality, or at least an interference experiment to observe the entanglement of these Hawking correlated pairs. And that's all I wanted to say. And thank you for your attention.
Okay, so thanks, Chris. So I would have on my own plenty of questions, but and I would show you other experiment to you. So This is not my role here. Yes. Yeah.
I'm a little mystified by what you want to learn about quantum mechanics or whatever by doing this fake Hawking radiation. After all, you're looking at the system that is basically non-relativistic quantum mechanics.
I'm afraid you're right. I'm afraid that we're not going to learn anything that we didn't already know about quantum mechanics. Because, like I said, a weakly interacting Bose gas is very well understood. We've tested many things about it, and putting it in this fancy flow situation is not going to be. In fact, it has been analyzed by Carusotto and others what it ought to look like, and we're just going to be. The best case is that we confirm these theoretical approaches. And I'm afraid we're not going to learn anything about trans-Planckian physics or the black hole information paradox, unfortunately. Unless we really prove that it's not as simple as ordinary quantum mechanics predicts. But
no question, I'm surprised.
Yes, Chris, so in this, at least in the microwave analog of this dynamical Casimir effect, there is always one way of seeing it, which is also, in fact, so my question, I guess, is the relation of these, at least this dynamical Casimir effect in the microwave domain with just broadband squeezing. And because in the original dynamical Casimir effect, there is of course this mechanical motion, and in the microwave version, it's really this modulation of the electric constant, and so this resembles very much broadband squeezing as is often known in optics. I mean, as is well known in optics. So I wanted to have your opinion about it.
I think you're quite right that you're modulating an index in a way that looks like parametric. That can be looks like it really formally it just looks like parametric downconversion. And I actually I visited their lab and I actually posed the same question to a guy, a theorist, I forgot his name, but he said, well, yeah, okay, but if you say that, you're in a way, this effect is impossible to see, because if you have a mirror, a physical, a real life mirror, where the electromagnetic field does not have a node right at the mirror, it actually leaks into the inside a little bit. If you start moving that, well, that's changing the index of something as well, right? You're taking space and you're just adding a little bit of index to the boundary conditions in which this electromagnetic wave lives. And that's not really any different, is it? That was his response. All right? So maybe this dynamical Casimir effect is really just a thing it's a theorist's toy, but we cannot really observe it in the laboratory. And by the way, the same objection can be made to what I just described in the BEC. Taking a BEC and modulating something is just a parametric effect. And we've already heard, somebody already mentioned Faraday waves. And actually, there's an earlier paper which didn't talk about the Casimir effect, but they talked about Faraday waves. They actually shook a BEC in a similar way and observed Faraday waves, which behaved in the same way. The only difference was they didn't look at the correlations as microscopically as we did. And someday you can hope that there will be a quantum correlation in these correlations. And that would be a real step forward, but it would just be a demonstration that we can do parametric oscillators with phonons.
Crystal clear. Michel?
Can you tell a bit more about the way you generate your pairs, correlated pairs?
The entangled one.
The origin of the entanglement.
Let me see. The ones here at the end. These. Yeah. Okay, they are produced in a. They're produced by a BEC in an optical lattice, The optical lattice changes dispersion relations in such a way that basically two atoms at one momentum can collide and produce two atoms at two other momenta. Okay? And since it's a collision, we're very sure it's a pairwise collision. Okay? So we're very sure that for a particle here, there's another particle here. Okay? Or at least the mechanism says that that's what should happen, and we can look at correlation functions and really see that. But we cannot guarantee that a single pair can be in a superposition of these two and those two. No, what I mean is, no, these two and those two. Okay, the outside ones are correlated and the inside ones are correlated. And can you really produce, we don't know, but we think that the bandwidth is such, well, if we look at the cross correlation, the bandwidth is such that there's nothing preventing that from happening. Nothing preventing an atom from being in both of those states at the same time.
If I may enter the discussion, it's a bit surprising that the quantum process doesn't produce the superposition of all.
Oh, it does. I'm sorry, it does, yes. In fact, strictly, before doing any selection, I should put a sum here and sum over all possible momenta in these bumps.
Including this one.
Including this one, okay, right.
Yeah.
But we discretize the problem by selecting just a narrow window which corresponds to one diffraction limited mode. Okay, but the real pair production looks like it's several modes. We're producing these p's in several modes. It looks a lot like what happens, in parametric down conversion in optics, right? You get these two rainbows, and it's a continuum of frequencies, and they are correlated in a pairwise way. And to do things like Bell's inequalities or other kinds of correlation experiments, people put pinholes to select the appropriate frequencies and get them to interfere, to do Bell's inequalities. And we're doing what amounts to the same thing. Except that we didn't know that there would be, we couldn't guarantee that this wasn't a statistical mixture. And we are now beginning to convince ourselves that it is not just a statistical mixture of those momentum states.
So you mean you can really exhibit entanglement witnesses?
Yes, I would claim that this is an entanglement witness.
Not yet successful, but soon.
Well, it's 2 sigma. It's 2.5 sigma, but yeah.
No other contribution. So thanks a lot, Chris.